Hi, my name is Megan Farrell, and our project is on the synthesis of ammonia from natural gas. Our team name is Team C.R.E.A.M. Carbon rules everything around me. First, we're going to go through some background information on the process. We're going to do a process overview. We'll continue on with the product and some information on the industry. Finish up with an economic evaluation and our recommendations.
Hi, my name is Tong Yin, and now I'm gonna talk about the background information. So our company is located at Philadelphia, Pennsylvania, and our company recently was requested to produce 99.5% pure ammonia from natural gas, with minimum of 90% mole conversion of feed methane into ammonia. Our plant design gave net profit value of negative $4,900 million, and some of the main challenges were mercury removal, water impurities removal, and high operating temperature of gas shift reactor, and some others. When it comes to industry process, safety comes first, and 75% of our employees are green belt at 6 Sigma or above, and there has not been any OSHA recordable in last 5 years. Now Blaze is gonna talk about the process overview.
Hi, I'm Blaze, and I'm going to talk to you a little bit about our process overview. So to begin, the feed comes from a storage tank at 80 degrees Fahrenheit and 400 psi. The main component in the feed is 90% methane. First thing we do is we fire heat the feed up to 800 degrees Fahrenheit. We do this in order to send the feed to the component removal section. The next step in the process is to remove the mercury and sulfur. It is important to remove the mercury and the sulfur from the feed because they can poison some catalysts we use downstream. That would render those processes useless. So as you can see, the feed enters the mercury removal, removes all of the mercury as the product continues on to a cooler. The cooler lowers the temperature of the feed so that the desulfurization process can occur. Again, the sulfur is completely removed and the feed proceeds on to the synthesis process.
Hi, my name's Maria, and I'm going to continue on to talk about the synthesis portion of our design. So this next up is the steam reformer, which uses methane to convert into carbon monoxide and hydrogen gas. Since this reaction is endothermic, we have a stream of steam entering into the steam reformer. Propane and ethane are both also used to react with the steam and convert into carbon monoxide and hydrogen gas to give a greater conversion of both these products. Next, I'm going to continue on to talk about the gas shift converter. This unit is a fixed bed reactor which operates at high temperature. It takes the carbon monoxide produced from the steam reformer and reacts it with water to give carbon dioxide and more hydrogen gas. This process is known as the water gas shift reaction. And now I'm going to continue on to talk about our first recycle stream. The products from the gas shift converter enter two cooling utility duties, where it enters the vapor liquid separator so that the unreacted water can be recycled back into the gas shift converter. This will increase the conversion rate of carbon dioxide and hydrogen gas. Next, Megan will continue to talk about the production section of the design.
Now I'm going to continue with the last step in the synthesis process. Pressure swing absorption is used to remove carbon dioxide and carbon monoxide for hydrogen purification. Carbon monoxide and carbon dioxide must be removed from the feed because it denatures downstream catalyst. This process works by the binding of molecules. Molecules with a low polarity and that are highly volatile essentially don't absorb at all to the catalyst, while molecules such as carbon monoxide and carbon dioxide readily bond to them. So in the process, as you can see, the feed gas comes in, and in the absorption tower, that's where the high pressure is, and that allows for the carbon monoxide and the carbon dioxide to bind to the catalyst, while the hydrogen is free to go out of the distillate. There's a regeneration time of about 30 minutes. So when the regeneration occurs, the catalyst will go from the adsorption tower to the desorption tower, which is a lower pressure tower. In the lower pressure tower, the carbon monoxide and carbon dioxide that is adsorbed into the catalyst can then desorb and be removed in the waste stream. The catalyst is then regenerated and will circulate back into the adsorption tower, where it continues to absorb more carbon dioxide and carbon monoxide to purify the hydrogen. There's also a second unit that is exactly like this one, so that there's never a downtime for the feed. So while this catalyst is regenerating, the feed gas can go to the next system and continue to purify hydrogen in the process. Now we have finished up with the synthesis process, and we can move on to the production aspect. The first step in the production is the Haber-Bosch process, which produces ammonia. Ammonia is produced from nitrogen and hydrogen. Our current feed had a great amount of hydrogen in it, so additional nitrogen was needed to add to the reactor to have a higher conversion. Exiting the reactor is a mixture of ammonia, nitrogen, and hydrogen. They're all in the vapor phase, so to be able to separate them, additional steps had to be taken. Now to continue on with the additional steps that need to be taken to separate the ammonia, we will go into the cooling process as well as the recycle stream. So the feed gas enters the converter as it was before with the nitrogen, and it's converted to mainly ammonia, but then also there's unreacted nitrogen and hydrogen. It goes through a set of coolers to condense the ammonia to a liquid form. This then enters the vapor liquid separator, where the ammonia exits the bottoms and the unreacted nitrogen and hydrogen go through the recycle stream and back into the ammonia converter. This was able to decrease the amount of nitrogen that we needed to put into the ammonia converter, and it also was able to provide a higher conversion rate. Now that we've finished up with the production aspect of the process, we can move into more information on the actual product and what industries and markets it's sold in. So as you can see here, we were able to achieve a 99.9% purity of ammonia. This means that it is ready to be sold to industry. So to get into a little bit of information about the markets, ammonia is second behind sulfuric acid in the largest chemical production. The markets that it typically sells to is fertilizer. As you can see, that consists of 85%. The main driver behind the ammonia production is the low cost of natural gas. Currently, it's around $2 to $3 per million BTU, but in the past 10 or 15 years, it's gone up as high as $13 per million BTU. So with the low prices right now, that's really pushing the market to create more and sell more to the fertilizer companies.
Hi, my name is YZ Long. From now, I want to talk about the economic variation. So for economic variation, we first set the price of ammonia is 70 cents per pound, and our sufficient ATROR should be 15%. And after our calculation, the total cash cost is $1.34 per pound, and ATROR is unable to calculate. It is because our ATRR rate is below than the minus 30%, and the Excel file only calculates till minus 30%. And for our required net bug is $1.53 per pound, and our net present value is negative approximately $4,900 million. And after we analyzing the cash flow model, the cash flow model has three primary factors. One is raw materials, second is utility, and third is fixed cost. And we found out that the raw materials has a very big portion of the cost, so we want to analyze more about the raw materials. And after we analyze the raw materials, we find the biggest portion is actually the water. It is because we're using the municipal water to convert to DI water, and it actually costs a lot. So we kind of have an idea to alternate method is for using river water instead of municipal water. So now this is our total cost for a plant. We first have the total capital cost. It's include the one-time purchase, for example, like equipment and the land fee. And the cost is $67 million. And next is total utility cost. And utility costs include the electricity and for refrigeration or heating. So the total cost is $18 million. And lastly, we have the operating cost. It's including the salary for the operator and also for the overhead fee. And this is $25 million. So the detail about this cost will be discussed in later for analyzing the IBL and OBL.
So for the IBL, we used Icarus software to input our parameters from which we got from sizing our equipment calculations. We took those parameters and put it in order to get the equipment cost for each unit. The contingency and the capital percentage were both set to 0 in Icarus due to the fact that the OBL equipment accounts for these. So if we didn't have them at 0, it would add it on twice. Now, the material of construction that we chose was, the first one is carbon steel. This temperature range, it goes from -20 degrees Fahrenheit to 600 degrees Fahrenheit. It's commonly used and it's the cheapest one. So we use this for any reactor that was within those temperature limits. For the ones that went above 600 degrees Fahrenheit, we use stainless steel 304L. Now that type has a maximum temperature of 1650 degrees Fahrenheit, and it's also very versatile, so it was an easy choice for us to go with. And it's decently cheap. After going and putting our parameters in Icarus, we got each equipment cost for the units. The most expensive one by far was the compressor. We have 2 units and it came out to around $25 million. And now Megan will talk to you about the OBL equipment analysis.
Now we're going to talk about the OBL. The first part of the OBL is storage for the feed and the product. We designed the storage tanks for the feed to hold up to a week's worth of natural gas. And we designed the product tanks to hold up to 2 weeks of ammonia. Bids were given by Professor McFadden for the pricing on this. Next, water purification is part of the OBL. The water that's coming in naturally has minerals occurring in it. Before the water can go through the process units, these minerals need to be removed through an ion exchange unit. Next was the utility cost. This was the price for anything that required cooling, heating, or refrigeration, so all of the coolers and heaters that we had. Next, we had our chemical prices. Nitrogen was definitely the highest cost for our chemicals, and that was used for the ammonia converter and was over $55 billion per year. Lastly, was our waste. We installed a flare system to burn off any hydrocarbons that were waste, and also incineration was used for any hazardous chemicals that were left over.
Yep.
Now we'll go into our conclusions and our recommendations.
So now I'm going to tell you a little bit about our conclusion and our recommendations. So based on our economic analysis, we decided that you should definitely not proceed with building this plant. As you can see, after the third year of capital cost, the fourth year starts, we would actually be running the plant, and once the utilities and the costs of waste and everything start kicking in, we lose money even more drastically. And so by the end of the 20th year, we would have lost $5 billion. So we definitely believe that we should not go on with building this plant. In terms of recommendations, we believe that we should further look into a different process design for the pressure swing absorption and removal of CO, because as you can see, over half of our utility costs was just trying to bring down the temperature of the stream so that we could separate the water out and then proceed to removing the CO and the pressure swing absorption. Additionally, we could look into selling some of our byproducts such as mercury or sulfur. They are 100% pure, so we should be able to sell those on the market. And in terms of material costs, municipal water was our largest expense by far, and so we could look into utilizing river water and cleaning it and returning it. And additionally, nitrogen was our highest material in terms of like a chemical cost, and so we could look into producing our own nitrogen or utilizing air. So in summary, we explained to you a little bit about our background in our company and about ourselves. We took a detailed look into the process overview of creating this pure ammonia. We looked at the product that we were making and how it could be used in industry. We also took a look at the economic evaluation and determined that we should not build this plant after all. And finally, some recommendations that potentially could put us in the right direction to actually building this plant and making a profit.